Hello, and welcome to this series on what? Oh, sorry. Sorry, you get so used to wearing these things these days. Forgot. Hello, and welcome to this series, the second episode in this series of Why the Universe is Quite Disappointing, Really, the antidote to inspirational astronomy videos. In the first episode, I demonstrated that stars are really not all that good at generating energy. And what I want to do in this video is to expand on that a little bit and look a little bit more at why it is that stars are basically so underwhelming. The reason they're underwhelming is because of the limitations of nuclear reactions. So what we need to do to understand this a little bit better is to go and look at the workings of the inner regions of a star like the Sun. Let's have a look in a little bit of detail at the nuclear processes that happen in the core of a star like the Sun. It's worth saying before I go on that different kinds of stars, especially stars of different masses, involve different kinds of nuclear reactions. And in any case, even in a star like the Sun, it's a bit more complicated than this just one process that I'm showing here. But this it kind of illustrates the main point, so I'm just going to simplify a lot. Incidentally, the graphic that I'm using here to illustrate the process is just something I ripped off from the internet. So the process is called the proton-proton chain, and this is actually only one part of it, but it's kind of the main part. So we'll focus on that. What you'll see is that entering stage left, there are 4 hydrogen nuclei. A hydrogen nucleus is basically a very simple nucleus. It's only one particle. It's a proton. The first step of the proton-proton chain is for 2 hydrogen nuclei, protons in other words, to collide and interact in such a way that they produce a deuterium nucleus. That's a nucleus of a heavy isotope of hydrogen called deuterium. Now, that involves one of the protons turning into a neutron, represented by the blue circle there, as opposed to the sort of mauve circle for the proton. That weak nuclear interaction that's involved in that produces the emission of a positron, beta plus, and a neutrino. Those are not really relevant to the main story here, but you don't really have to pay attention to them, but I introduced them basically to point out that this is a weak nuclear interaction for good, and its name is there for good reason. The most important thing about this, however, is the fact that merging 2 protons to make deuterium is a very difficult process because deuterium is very fragile. In the dense and hot environment of a star, it's easily broken up. So you lose the deuterium almost as rapidly as you create it. And so it's a very, very, very slow process. You'll see that the time scale is 10 to the 9 years. That's 1 billion years. And this is basically why stars operate extremely slowly. When it comes to nuclear burning, a star is very much a slow cooker, and it's limited basically by this deuterium problem. It's actually a design fault if you think about it. Anyway, once you've got enough deuterium hanging around, you can another proton can kind of sidle up from the side to this deuterium and attach itself to make a light isotope of helium, helium-3. That process is very rapid, and it leads to the release of some energy in the form of a photon, indicated by the gamma with the red squiggly arrow. Now, helium-3 is not the stable, familiar form of helium that we know and love. In order to go further along this process, we need another helium-3 to collide with the helium-3. that we've already got. So that involves another branch of the chain, as shown in this graphic. When you collide two helium-3 nuclei together, then you can create helium-4. That's energetically very favorable to do. And that process results in the spitting out of two protons, hydrogen nuclei again. Now, if you just look at that, you'll see that, that there are two hydrogen atoms which have appeared in the middle of this process, and two are released at the end. So those two are not involved in a net sense in the process. If you just look at the end point and the beginning, you'll find that this process basically involves taking 4 protons and making a single helium-4 nucleus. Now, there are other reactions which do this, and the whole process is actually quite complicated. But nevertheless, what happens is that the basic result is that 4 protons become a helium nucleus, and some other stuff that we don't really care about. Okay? Now, all of these complications is a good illustration of how physicists actually work in dealing with complicated things like this, because the helium nucleus has a very well-defined mass. And the helium nucleus is the end point of this process. Protons have very well-known masses as well, and those are the start points. So we can basically cut out all of the stuff in the middle and get some understanding by just studying what happens at the beginning versus what comes out at the end. And if we look at the mass of a helium nucleus compared to the mass of 4 protons, we'll find that actually the mass is slightly different. And the reason why those masses are slightly different is because there's a difference in energy. Some energy has been released in this process. And that's why it's called a nuclear burning. It's nuclear fusion, but it's actually essentially burning material in some sense. And we can interpret that difference in mass through the most famous equation in all of physics. Oh, hang on a minute, that's not right. There, that's better. E equals mc squared, the best known, perhaps not the best understood equation in physics. But this basically tells us that if there's a difference in mass between the beginning and the end of a process, then there's also a difference of energy. So we can actually work out how much energy is liberated by simply comparing the masses of the end point and the starting points. Okay, so I'm not going to go through that. You can look up the mass of helium and the mass of protons if you like and do that calculation. I'm just going to tell you what the answer is. And the answer is that if you take 1 kilogram worth of hydrogen nuclei, protons in other words, and cook it entirely into helium-4, that will liberate 6.6 times 10 to the 14 joules. Now, a joule is a unit of energy, which is in the SI system, which is used throughout the civilized world, but perhaps not so much in America. Now, so 1 kilogram produces that amount of energy. So you can ask the question how much energy is kind of available to be liberated in a star like the sun. Well, let's just assume that the sun is made entirely of hydrogen. It's not actually, but let's just assume that for the sake of argument. And we know, because I sprang it on you in the first episode, that the mass of the sun is about 2 times 10 to the 30 kilograms. So we can work out how much energy is available very easily by saying it's 10 times 10 to the 30 kilograms multiplied by how much energy you get per kilogram, which is the number that's at the top of the page. So if you work that out, it's 2 times 10 to the 30 times 6.6 times 10 to the 14 joules, and that's 1.3 times 10 to the 45 joules. That's how much energy is potentially there to be liberated by nuclear processes in a star like the sun. Now, we can look at the sun and work out how much energy it's actually managed to liberate. We can do that also very roughly, very simply, by noting that we think the current age of the sun is about 4.5 billion years. I've actually put 4.6 times 10 to the 9 years. That's actually, there's some debate about that, but it's a ballpark figure. For the following calculation, we're going to need that lifetime in seconds. So we need to multiply that by how many seconds there are in a year. Now, if you've never counted them, I have, and I can tell you that the answer is about 31 million seconds in a year. That's 3.1 times 10 to the 7 seconds in a year. So if you work out the age of the sun in seconds, it's about 1.4 times 10 to the 17 seconds. So what? Well, the watt is a unit of power, and its power is energy per unit time. So its units are actually joules per second. We already know the power output of the sun because I told you it in episode 1. It's 4 times 10 to the 26 watts. In other words, 4 times 10 to the 26 joules per second. So we can work out if the sun, this is a rough approximation, of course, if the sun has been radiating at that power for its entire lifetime, how many joules has it actually radiated? So the answer is roughly 4 times 10 to the 26 watts times the lifetime in seconds. Joules per second times seconds will give you joules. And the answer for that calculation is 5.7 times 10 to the 43 joules. So now we can do a really simple calculation and say, like, of all the energy that's potentially available to a star to be liberated through nuclear burning, what fraction has it actually managed to do that with? So the answer to that is the ratio of those two numbers I've just calculated. It's 5.7 times 10 to the 43 divided by 1.3 times 10 to the 45, which comes out as about 0.044, 4 or 5%. Now, there are approximations in that I've mentioned before. The sun is not entirely made of hydrogen, so it doesn't have all of that mass available to be burnt. But nevertheless, it's a few percent. It's not most of the energy, most of the available energy. Now, I think you're probably saying, well, this is actually, if you're going to say that that's disappointing, then that's a bit unfair because the sun, I know it's 4.6 billion years old, but maybe that's quite young for a star. And, if you just let it run, it'll gradually cook more and more and make more and more helium and use up more and more and more of its energy. And so that number will rise to, sort of a large, maybe 80%, 90% given enough time. Well, the answer is no, it won't. Astrophysicists have been studying stars for a very long time, and they have very accurate and precise models for the evolution of a star and for the structure inside a star as determined by the various physical processes, including nuclear energy generation. And they all suggest that the sun will actually only live for another 5 billion years or so. So the total lifetime of a star like the sun is probably about 10 billion years. Again, a very rough figure. So that means in 5 billion years or so, the sun will die. You shouldn't worry too much about that. I'm not worried about it because I'll be retired then. But nevertheless, if you sort of double the lifetime of the sun, you'll just double that number in terms of the fraction of energy is released, and it might go up to around 10%. So basically, in the whole lifetime of a star, it struggles along trying to generate energy and release energy in radiation from this vast reservoir that it has through a painfully slow and inefficient process. And it only ever gets to use up about 10% of the available resource before it dies. I think that means that a star like the sun is definitely a bit disappointing. So I thought I'd just add a little postscript to that, which is just to say why it is that a star can't access all of the fuel that it potentially could in order to keep itself burning for longer than it can. And the answer is because everything is confined to the center of the star. The nuclear reactions go on there. They gradually produce helium, which is a waste product, but that waste helium is not distributed throughout the whole star. It accumulates in the center, rather like ashes accumulate in the grate of an open fire. And as they accumulate, unless you clean them out, they gradually make the fire burn less efficiently, and then it goes out, basically. So that's what happens with stars. Helium accumulates in the core and actually makes the nuclear processes struggle even more than they did already, and they end up just not being able to keep the star going anymore. So there you have it. My summary of stars is basically they struggle along through their lifetime unimpressively, not doing a particularly good job at what they're supposed to be doing, and then they die. If you think about it, that's a pretty good metaphor for human life. And talking about life, I'm actually going to do a little bit about life in the next episode.